All right, in this video, I'll be talking about resolvents for polynomials. And we're pretty much going to talk about how resolvents allow us to reduce the problem of solving higher degree polynomials to solving simpler, lower degree polynomials. This was a technique that was used historically, which led to solutions to cubics and quartics. And this was also meant to be used to pretty much try to find the solution to a general quintic, which ultimately failed, as we will see why later on. So, a resolvent is a polynomial constructed from the roots of a given polynomial in such a way that the roots of our resolvent pretty much give important information about the original roots. And by solving this resolvent, typically, usually always found in a lower degree, as that is the whole point of a resolvent, we indirectly obtain values that help reconstruct the roots of the original polynomial. So to put it simply, our polynomial p of x we could say that it is a general polynomial an, xn, and then plus an minus 1, xn minus 1, plus so on up until the constant a0. And the roots of p of x are r1, r2, and so on up until rn, given by the fundamental theorem of algebra. And a resolvent polynomial is built using expressions involving these roots, often combinations that involve symmetry of sums, products, and anything that has to do with symmetry. And if we were to go ahead and make such a resolvent, we would get a polynomial r of y, which is equal to bn y n minus 1 plus so on up until b0. And what we're going to notice is that bn up until b0 is going to be built specifically with p of x's coefficients. Like b of n could be, for example, an times an minus 3 plus an plus 2, an plus 6 squared, and so on. That's an example of what bn could be. And pretty much the reason we use a resolvent or how we even get a resolvent is simply Vieta's formulas. And Vieta's formulas basically states that the first, let's say, an minus 1, xn minus 1, is always going to be the sum of the roots. r1, r2, plus up until rn is going to be equal to negative an minus 1 over an. And the double product is going to be r1, r2, plus r1, r3, and so on up until let's say 1, rn, right? And it's going to be either 1, 2, or 3 for r1, rn. And this is pretty much going to be a n minus 3 over a n, and so on. That's pretty much how we use the symmetry of Vieta's formulas and end up with a resolvent. So the importance of resolvents, right, is that they are symmetric functions of roots, and they are very important to substitution techniques, and are very important to substitution techniques, and of course, Galois theory itself. And the reason this matters is because the solvability of polynomials via radicals depends on whether the equations governing certain combinations of its roots can be reduced to solvable forms, which is exactly what a resolvent reveals. And historically, resolvents always ended up appearing in Cardano's method for cubics and Ferrari's method for quartics and pretty much every other method for solving higher degree polynomials. So let's go ahead and look at two examples of a cubic resolvent. So we have our polynomial p of x is equal to x cubed plus px plus q. We're going to look at a depressed cubic for this so that we don't overcomplicate things. And the resolvent that we found in the previous video, r of y, was given by y squared plus 27qy minus 3p cubed, or to fully expand it, minus 27p cubed. And we see how our resolvent r of y pretty much consists of p and q in its coefficients. And solving for r of y and solving for the roots, we would pretty much have r1, or actually let's say y1 is equal to pretty much the square root negative 27 q plus dot dot dot, right? And then over 2. And y2 would be equal to negative 27 q minus the square root of dot 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 over 2. And solving for one of the roots, right, would be the cube root of y1 plus the cube root of y2 over 3. And if you want to see the whole derivation of this resolvent specifically, you could go ahead and look at my other video, pure resolvent derivation, and yeah. So for the other resolvent, which is in Cardano's method, is a very straightforward process, because for p of x is equal to x cubed plus px plus q, Cardano set x equals u plus v, which led to a resolvent r of u is equal to u squared plus qu minus p cubed over 27. And solving for the roots of u, we would see that u and v are going to be built off of cube roots for our equation. Because, of course, r of u is simply a quadratic. So that is the whole point of a cubic resolvent, right? We lower it down to a lesser degree, namely a quadratic, and then solve for the roots. But in the example of Cardano's method, we usually get u squared plus qu, but that is because if we just assume our solution is a cube root, right? That lowers the degree down, but if we were to actually just have u plus v, the degree would be a 6th degree polynomial, which is what I mean by sometimes resolvents will lead to a higher degree polynomial. Because here we start off with a cubic, but then we end up with a 6th degree polynomial, or a sextic. But of course, using the substitution, right, where we have u cubed is equal to t, and then u to the 6 equals t squared, we could solve a quadratic. And then once we solve for t, we just take the cube root of both sides and then solve for u, which then we get u is equal to the cube root of t. So that's pretty much what I meant earlier by sometimes resolvents lead to higher degree polynomials. And sometimes they are easily solvable in the case of Cardano's method, where we get a 6th-degree polynomial that can be reduced to a quadratic with a simple substitution. So now let's go ahead and look at the quartic. So we have p of x is equal to ax to the 4 plus bx cubed plus cx squared plus dx plus e. We're going to use Ferrari's method and we're going to see what our resolvent looks like. So Ferrari pretty much decided to depress the quartic so that we get a depressed quartic, and then managed to simply use the advantage of only having just one linear term and two even degree terms. But here we're just going to go ahead and use all terms, which is the general quartic. And the idea that Ferrari imposed was we complete the square in terms of x squared. And what we first always do is divide by a. So pretty much just factoring out an a. So we have x to the 4 plus b over a x cubed plus c over ax squared plus d over ax plus e over a. And we're just going to focus on the inside now, the parentheses, x to the 4 plus b over ax cubed, and so on. What Ferrari did was complete the square for these three terms, the x to the 4, x cubed, x squared. And this resulted in x squared plus b over 2ax squared, and then plus c over a minus b squared over 4a squared x squared plus d over ax plus e over a. And he introduced a new variable, y, into this expression right here, which became x squared plus b over 2ax plus y over 2. And you could choose y to be anything. It could be y over 2, y over 4, y over 3. It doesn't really matter. It's up to you and your preferences and how you want your resolvent to be, as you could pretty much make infinitely many resolvents using Ferrari's method, but they're all going to produce the exact solution, and pretty much the exact same solution is what I'm trying to say. And pretty much including y and expanding everything, we are going to get plus c over a minus b squared over 4a squared minus y x squared plus d over a minus b over 2a y over 2ay times x, and then plus e over a minus y squared over 4. And now, since we have a new free variable y, what Ferrari did was pretty much look at the quadratic right here that we have, and what he did was use the discriminant of this quadratic and set it equal to 0, because this right here could be transformed into a perfect square, where we pretty much had d over a minus b over 2ay squared minus 4 times, and then c over a minus b squared over 4a squared minus y times e over a minus y squared over 4. And he set that equal to 0. And pretty much after some algebra, right, this can be expressed as a cubic in terms of y, which would be y cubed minus c over a y squared plus b d over a squared minus 4e over a, 4e over a, y, and then plus 4ce over a squared minus b squared e over a cubed minus d squared over a squared is equal to 0. And here we can go ahead and use Cardano's formula to solve our cubic in terms of y. And when solving for the solution in y, pretty much any solution of y will automatically make this quadratic right here a perfect square, because the discriminant is simply equal to 0. And we see that once we solve this cubic, the quartic factorizes into quadratics, which we could pretty much then use the difference of squares, or if no roots exist, we're going to get two quadratics that give out imaginary solutions. And as we see, like, the structure of the cubic resolvent here is derived from pretty much all of the coefficients of our quartic. And we can also make a lot of other resolvents simply from using the roots, right? So we have roots R1, R2, R3, and R4. And these roots are characterized by Vieta's formulas. R1, R2 plus R3 plus R4 is equal to minus B over A. And R1, R2 plus R1, R3 plus R1, R4 plus R2, R3 and R2 or plus R2, R4 plus R3, R4. And that is equal to C over A. And then we have the triple roots, or pretty much the triple product of the roots, R1, R2, R3, plus R1, R2, R4, plus R1, R3, R4. And finally, R2, R3, R4 is equal to negative D over A. And finally, the product of all the roots, R1, R2, R3, R4, is equal to E over A. And what we can do is we notice that we have R1, R2, R3, R4, and we can make a system of equations, or we could go ahead and make a resolvent for our expression. And we can say, right, in order to create a resolvent, we need to say, let's assign y1 to be equal to a times r1 plus r2 minus r3 minus r4, and then y2, y3. And then we will just pretty much like use some sign changes, which will be minus r2 plus r3 minus r4. And then finally r1 minus r2 minus r3 plus r4. And you're wondering, right? Okay, we only have three equations. How do we isolate r1, r2, r3, and r4? Well, we could use the sum of all roots. Minus b over a is equal to, or we could say minus b is equal to a times r1 plus r2 plus r3 plus r4. And we see now, if we go ahead and solve for r1, we're going to go ahead and get a mix of solutions, right? So if we just simply add all four solutions and look for r1 by itself, what we will get is y1 plus y2 plus y3 minus b is equal to 4a r1. And since we have r2 plus r2, that is 2 minus 2r2, which these cancel out. And we see that they cancel out and these cancel out, simply giving us r1 is equal to minus b plus y1 plus y2 plus y3 all over 4a. And of course, this is somewhat different from our quadratic form or quartic formula that we know. And of course, this is different from the quartic formula that we usually are used to seeing, as the one I derived in a video a long time ago. And if we go ahead and look at the resolvent that we get from these expressions, we will see that pretty much the cubic in terms of y will be y cubed minus 3b squared minus 8ac times y squared plus 3b to the 4 plus 16a squared c squared minus 16a b squared c plus 16a squared b d minus 64a cubed e y minus b cubed plus 4abc minus 8a squared d all squared equal to 0. So pretty much we see that this is going to be our resolvent for r of y. And we can set r of y equal to 0 if p of x equals 0, so we could solve for the roots. And as we see, our resolvent is once again constructed off of a, b, c, d, and e, as all coefficients of our resolvent polynomial y involve a, b, c, d, and e. And of course, as we already know that pretty much our solution for p of x is going to just be r1 is equal to minus b plus y1 plus y2 plus y3 over 4a is going to be our solution to p of x, where we can easily solve for y cubed plus all of this and simply get y1, y2, and y3 via the cubic formula, Cardano's method, any method that you would feel comfortable with doing. And of course, you could make a lot of resolvents just from the quartic because of the very nice properties that come with it. We'll just go ahead and look at one more specific resolvent. So let's just look at a depressed quartic plus px squared plus qx plus r. And pretty much what we're going to do is we assign z1, z2, and z3 to be pretty much combinations of the double products of the roots. So you'll have r1, r2 plus r3, r4, and then r1, r3 plus r2, r4, and r1, r4 plus r2, r3. And if we go ahead and just find the resolvent in terms of z, we will get z cubed minus p z squared minus 4rz plus 4rp minus q squared is equal to, well, actually, let's just say that it is equal to r of z. And here we can see that, we can pretty much see that our resolvent is built off of our cortex coefficients, p, q, and r. And what I want to do right now, right, is I'm pretty much going to list every kind of resolvent for the quartic. So you're going to see a few that I may have went through and some that I may have not went through. So actually, I'll just keep that one there. And the other ones I'm going to list, which are going to be z cubed minus p z z cubed minus p squared plus 8r z squared plus 16r squared plus 2rp minus 2p q z minus q squared minus 4rp squared. I'm not going to write equals to 0. And we're going to look at Ferrari's resolvent, which is 8z cubed plus 20p z squared plus 16p squared minus 8r z plus 4p cubed minus 4pr minus q squared, and the other resolvent, which is going to be z cubed plus 2p z squared plus p squared minus 4r z minus q squared. And pretty much we have like a lot of different resolvents, right? Along with the other two that I showed earlier, we can still see that we're always going to get different resolvents that are pretty much going to help us solve our quartic. Though the formulas may be different, they may look extremely complicated, some may look neater than others, but nonetheless, they are still going to at least help us with understanding our polynomial's behavior. And that's pretty much the important part about resolvents. Like if we solve for z in any of these, we're going to be able to solve our quartic via radicals. And finally, we're going to go ahead and look at the quintic, right? So p of x is equal to ax to the 5. Actually, I'll just go ahead and look at a depressed quintic, which will be x to the 5 plus p x cubed plus qx squared plus rx plus s. And to solve this quintic, right, we don't have a general formula yet, or there probably never will be one. But this quintic is given its solvability off of a resolvent called Cayley's resolvent. And pretty much the polynomial is going to be, let's say, some value, or pretty much something that has a lot of long terms. Let's see. Let's just label it capital Z. and it is going to be squared minus 1024 z delta, right? And z, or capital Z, is pretty much defined by a cubic z cubed minus 20r plus 3p squared z squared minus 8p squared r minus 16p q squared minus 240 r squared plus 400 sq minus 3p to the 4 z, and then the constant will be minus p to the 6 plus 28p to the 4 r minus 16p cubed q squared minus 176p squared r squared minus 80p squared sq plus 244 or 224 prq squared minus 64 q to the 4 plus 4000 p s squared, and finally plus 320 r cubed minus 1600 r sq. And delta is going to be, of course, some long expression, just mainly a constant, which is going to be an extremely long expression, which I'm not going to fully write down. And what this tells us is that it allows us to test if a quintic is actually solvable. And if it is the case, then that means that this 6th degree polynomial here is going to need to have a rational solution in order for our quintic to be solvable by radicals. So this is just the main common resolvent that is widely known. If you ever go to study quintics, you're going to always end up seeing that Cayley's resolvent is important, because most of the time we cannot find a resolvent of lesser degree for a quintic. So that's just the overview of the quintic and resolvents and why there isn't a formula for the quintic. So we've already gone through every case of a resolvent for a polynomial, and we've also looked at different kinds of resolvents. And Galois later formalized this, showing that the resolvent's solvability relates directly to the structure of the Galois group of our original polynomial. Galois later formalized this, right, showing that the resolvent's solvability relates directly to the structure of the Galois group of the original polynomial. And most importantly, like, the resolvent has a solvable group, then the original equation is solvable by radicals. And if not, as it is with most quintics and higher degree polynomials, no sequence of resolvent reductions will lead to a radical solution. Meaning that if you have, let's say, the Bring-Girard form, p of x is equal to x to the 5 plus p x plus q, no matter how many times you try to find the resolvent, even if you reduce it to a z to the 4 plus dot 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 plus some constant c equals 0, and you reduce this to a lower degree, you will not be able to solve it by radicals if the quintic does not have a solvable Galois group. So resolvents aren't really just computational tricks. They pretty much reflect specifically, deeply, and tell us a lot about algebraic properties that a polynomial has that we wouldn't notably know simply just from looking at the polynomial. Like if I tell you, go ahead and solve x to the 6 plus 6x squared plus 2x plus 1 is equal to 0, you wouldn't know what to do because you don't know if it's a solvable 6th degree or not. But if you find a resolvent, it will tell you whether this exact 6th degree polynomial is solvable by radicals, or you could just look at its Galois group. So yeah, pretty much polynomial resolvents are very powerful auxiliary equations built from carefully chosen combinations of a polynomial's roots. And solving these lower degree polynomials help reveal the roots of higher degree polynomials. They were pivotal in the historical development of algebra, leading ultimately to the birth of Galois theory. So yeah, pretty much thank you for watching, and hopefully this was a vague intro to resolvents. Thank you for watching and have a good day.